Hi everyone, sorry these are getting posted a little bit later than normal. We'll start with number 27 from section 5.2. So it says, let A be a 3 by 3 matrix for given V1, V2, and V3, as well as W. It says, show that V1, V2, and V3 are eigenvectors of A. Note A is the stochastic matrix studied in example 3 of 4.9. Okay, so let's define matrix A, be the matrix given in the text. So this is 0.5, 0.2, 0.3, 0.3, 0.8, 0.3, 0.2, 0, and 0.4. Let's just confirm that all the columns add to 1, which they do. Okay, so A is defined. I'm now going to take A times V1. V1 is a 3 by 1 vector, which is 0.3, 0.6, and 0.1. And we get 0.3, 0.6, 0.1. So that means that V1 is an eigenvector with eigenvalue equal to 1. We'll try that again now with the vector 1, negative 3, 2. And we get 1/2, negative 1/2, 1. So that means that that's also an eigenvector with eigenvalue 1/2. And finally, we'll try our last one, negative 1, 0, 1. And looks like we have multiplied by 0.2 to get that. So we've multiplied by 1/5. So we now know our eigenvalues that are associated with each of those. So that's part A. Showing them simply means multiplying. If we were to write something down, I suppose we would say 27A, we would say that A times V1 equals lambda times V1. And lambda in that case was 1. And A times V2 equals, why don't we call that lambda 1 and lambda 2? Lambda 2 times V2, and the lambda in that situation was 1/2. So lambda 2 equals 1/2. And then we can see that for the last case, and lambda 3 would be 1/5. Okay, part B. Let x naught be any vector in R3 with non-negative entries whose sum is 1. In section 4.9, x naught was called a probability vector. Explain why there are constants C1, C2, C3 such that x naught can be written as, okay, so let's write that down. We want to explain why x naught can be written as C1, V1 plus C2, V2 plus C3, V3, where those are the three eigenvectors given. Compute W transpose x naught and deduce that C1 equals 1. Okay, so let's play with that a minute. So first of all, let's investigate the three vectors that we were given and whether or not those are linearly independent. If we have a set of three linearly independent vectors, then those independent vectors must span all of R3, and therefore any vector in R3 can be written as a linear combination of these three vectors. So there's the three vectors in a matrix. I'm going to ref it and show that it becomes the identity. So my explanation would be the matrix V1, V2, V3 is row equivalent to the 3 by 3 identity. Therefore, by the invertible matrix theorem, the set V1, V2, V3, V3 is linearly dependent. Linearly independent. Therefore, they form a basis for R3, and any vector x naught can be written in terms of those vectors. Okay. They asked us now to compute W transpose times x naught. W transpose times x naught. So that's a little odd. So if W is the vector 1, 1, 1, then W transpose is the vector 1, 1, 1. We want to multiply that by this x naught, whatever x naught is. So you could say alpha, beta, and 1 minus alpha minus beta. All right, so that would be W transpose times x naught. So this is a 1 by 3 times a 3 by 1. So this would be alpha plus beta plus 1 minus alpha minus beta, which gives us 1. So how does that allow us to deduce that C1 equals 1? Well, that is strange. I'm not sure why that allows us to deduce that C1 equals 1. I mean, we can compute it, but How does that get us what we need? Let me look this up in the solutions. Let's see where if there's anything useful in there. So it's 5.2, number what? Number 27. Okay, here we go. See, all right, so, oh, they didn't want us to actually, I see. They didn't want us to actually compute it. They wanted us to do it more theoretically. Since x0 and v1 are probability vectors, and since the entries in v2 and v3 sum to 0, the above equation shows that c1 equals 0, or c1 equals 1. Interesting. Okay, fine. Although I don't really know that we need that. We could also just start with our x0, whatever. Okay, so for k equal 1 to define x sub k as a to the k equals x0, so we have that with x0 as in part b. Show that xk approaches v1 as k increases. All right, basically what we're doing here is we're saying that xk can be written as c1 is 1, I guess, so c1 times lambda 1 to the k times v1 plus c2 lambda 2 to the k v2 plus c3 lambda 3 to the k v3. And here's what we observe back from the top. Look, lambda 2 is a half and lambda 3 is a fifth. As k gets large, those go to 0, right? If c1 is 1, that means xk approaches 1 times 1 to the k times v1. So xk is going to approach v1. Okay, so that's sort of what they were trying to kind of get us to do a Markov chain using an eigenvalue, an eigenvector. Okay, next up would be number 1, 16, and 24 from section 5.3. Let's start with number 1. 1, 16, and 24. For number 1, it says P and D are given. So P equals 5, 7, 2, 3, and D equals 2, 0, 0, 1. And A equals P, D, P inverse. They want us to compute A to the fourth. Okay, so all we have to do here, A to the fourth equals P, D to the fourth, P inverse. Okay, P we have 5, 7, 2, 3. D to the fourth we learned is really just the entries on the main diagonal to the fourth, so it would be 16, 0, 0, 1. And P inverse we can compute pretty quickly. Our determinant is 15 minus 14, which is 1. That's convenient. We get 1 over 1 outside. Flip A and D, their positions, and negate B and C. Negative 7, negative 2. So our inverse is just that matrix. 3, negative 7, negative 2, 5. If we do the matrix multiplication by hand, just for exercise, we get 5 times 16 plus 7 times 0, that's 80. 5 times 0 plus 7 times 1, that's 7. 2 times 16, 32, plus 3 times 0, that's 32. And then 2 times 0 plus 3 times 1 is 3. We have to multiply that by 3, negative 7, negative 2, 5. 80 times 3 is 240, minus 14, so 226. 80 times negative 7 is negative 560, plus 35 is negative 525. 32 times 3 is 96. 96 minus 6 is 90. And 32 times negative 7, oh boy. 32 times 7, 1, 4. 7 times 3 is 21. 224. So negative 224 plus 15. So that would be negative 209, right? Okay, moment of truth. Let's go to the calculator and see if I did that right. So we're trying to use a theorem from the section to do something that we could basically do very quickly with calculator. So 5, 7, 2, 3 times d 2, 0, 0, 1 raised to the 4th times p inverse. Gives us 226, negative 525, 90, and negative 209. There we go. I still know how to do arithmetic. Okay, 16. The question is, we've got directions there. We've got a matrix, call it matrix A. It's 0, negative 4, negative 6, negative 1, 0, negative 3, and 1, 2, 5. And we are told in the directions that lambda equals 2 and lambda equals 1 are both eigenvalues. The directions are to diagonalize it. So we're going to try and write A as P, D, P inverse. All right, let's go to it. All right, so let's define A to be the 3 by 3 matrix. 0, negative 4, negative 6, negative 1, 0, negative 3, 1, 2, 5. Let's take A minus 2 times the 3 by 3 identity. F that augmented with 0. So right now we are finding the eigenspace basis associated with lambda equals 2. Excellent, it's two-dimensional. Okay. Right. So for lambda equals 2, we see that x1 equals negative 2x2 minus 3x3. x2 is free and x3 is free. Just to review, this is me writing this in parametric vector form. So this eigenspace is two-dimensional. That must mean that lambda equals 2 must occur twice in the characteristic polynomial. Let's check that. Determinant of A minus lambda times I. That. Factor it. Good. Okay, so lambda equals 2 does appear twice. So algebraic multiplicity is 2. Geometric multiplicity is also 2. All right, that's looking good. So the basis for this eigenspace would consist of these two vectors. All right, now for lambda equals 1, we're going to go back and do the whole process again, basically. I'm just going to literally repeat everything, but kind of change my numbers. So A minus 1i. Now we're going to ref our answer augmented with 0. We see one free variable, right? We see one non-pivot column, so let's pull this over. So for lambda equals 1, we have x1 equals negative 2x3, x2 equals negative x3, and x3 equals x3. So our eigenspace basis is negative 2, negative 1, 1, and that's the basis vector. So P is made up of each of these eigenvectors. This set is linearly independent. So P is full of eigenvectors. D contains the eigenvalues repeated according to their multiplicities. So 2, 2, 1. Zeros everywhere else. It's a diagonal matrix. And P inverse could be found on the calculator. Let's confirm that our work is right by taking PDP inverse. And, oh, by the way, this can be diagonalized because there are 3 linearly independent eigenvectors, or we can see that the algebraic multiplicity equals the geometric multiplicity for each of the eigenvalues. Okay, P is negative 2, negative 3, negative 2, 0, 1, and 0, 1, 1. E is 0, 0, 2, 0, 0, 0, 1. And we're going to try to do P times D times P inverse and see does that equal A. Uh-oh, we have a problem. I typed something wrong. 0, negative 3, 0, 1. Oh, there's the problem. This should be a negative 1. P times D times P inverse. So no, we're still wrong. This is not good. P times D times P inverse. That A? That's A. There we go. Okay, so careful how you type. And then remind me if you do that on a quiz that I need to be gracious with you as I was expecting you to be with me. All right, so we diagonalize that. And then 24 is the last one. A is a 3x3 matrix with 2 eigenvalues. Each eigenspace is one-dimensional. Is A diagonalizable? Okay, great question. The answer is no. And that's because if there are only 2 eigenvalues, that must mean that one of them must occur with multiplicity 2. In other words, we must have some situation like this. That would be the characteristic polynomial. But if each eigenspace is one-dimensional, that means for at least one of these, so for some eigenvalue, we'll call it lambda 1, the geometric multiplicity must be less than the algebraic multiplicity. Does that make sense? For algebraic is 2, and the eigenspace basis only has 1 vector, then geometric multiplicity is less, and we don't have 3 linearly independent eigenvectors. Therefore, it cannot be diagonalized. All right, that's it. We'll have a review day next class, and we will be ready for the final.